Let's suppose that we have a linear transformation from a vector space V into a vector space W. Then let's do a picture. Here we have the vector space V, and here we have the vector space W. Since these are vector space, that every vector space has a special element called the zero vector. Here we have also the zero vector. And then we're going to define the kernel of T, sometimes denoted like K of T, as the set of vectors V in the domain such that T of V is the zero vector in the codomain. That means that is the collection of vectors here in the domain that goes into the zero vector in the codomain. It is easy to show that this is a vector space, this is a subspace. Kernel of T is a subspace. And we already have seen this for matrices. When we have a matrix A, right, let's suppose that we have an n by m matrix. Then we have seen that we can define the transformation T of A of x equal to A times x. And this transformation T of A goes from C to the m into C to the n. And we have defined the null of A. The null of A is just essentially the kernel of T of A. Then it is nothing new. The null of a matrix is the kernel of the transformation T of A given by T of A of x equal A times x. Something interesting about a transformation is that we can check if a linear transformation is injective. Remember that a function, let's say a, b, c, 1, 2, 3, let's consider this function, f. A function is not injective when you can find two elements in the domain that go to the same element in the codomain. Then this is an example of a not injective function. And a function is surjective when every element in the codomain gets reached by an element in the domain. Then surjective means that let's say for every y in the codomain, we can find x in the domain such that f of x equal y. That means that surjective, when you see the picture, is that no element in the codomain is left out. Then we have the notion of injective and surjective. We have that if the kernel of a transformation is not just the zero vector goes to the zero vector, but if we can find another vector that goes to zero, then we have two vectors that goes to the zero vector, then the transformation is not injective. It is not straightforward, but it's easy to show that if the kernel of a transformation is just the zero vector, then the transformation must be injective. Let me write that down. A linear transformation is injective if and only if the kernel of T is just the zero vector. That means, this means that the dimension of the kernel of T is 0. Let's start by doing an example with a matrix. Let's suppose that we consider the matrix A equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Then the transformation T of A, in this case, is a transformation that goes from C4 into C3. And then actually from here we know that the kernel is not going to be just the zero vector, because when we compute the null of A, we are computing, we are solving a homogeneous system with 4 variables and 3 equations, and therefore there must be a free variable. That means that the dimension of the null of A, which is the dimension of the kernel of this transformation, is not going to be 0. Let's find the kernel and let's find the dimension of the kernel, which is, in this case, is the nullity. Then to do this problem, we have to solve the system x plus 2y plus 3c plus 4w equals 0, 5x plus 6y plus 7c plus 8w equals 0, 9x plus 10y plus 11c plus 12w equals 0. And then we end up doing row reduction to this matrix. 1, 2, 3, 4. I'm going to be lazy and I'm not going to write the last column of zeros. I'm going to just know that there is a column that I'm not writing and it's a column of zeros. 5, 6, 7, 8, 9, 10, 11, and 12. When we do row reduction, we get that the reduced echelon form of this matrix is the matrix 1, 0, negative 1, negative 2, 0, 1, 2, 3, 0, 0, 0, 0. Remember that I'm being lazy and I'm not writing the last column of zeros. Then this system is equivalent to this system. X minus C minus 2w equals 0, and y plus 2c plus 3w equals 0. Then we have that c and w are free variables, and then we need to write the basic in terms of the free, and then we have that x is c plus 2w and y is negative 2c minus 3w. And remember that the null of A, which is the kernel of this transformation, is a subspace of C4. It's built out of vectors in C4. Those vectors are x is c plus 2w. This is negative 2c minus 3w. C is free variable and w is a free variable, such that c and w are complex numbers. Then this can be written in this way. This is c times 1, negative 2, 1, 0, plus w times 2, negative 3, 0, 1, such that c and w are complex numbers. And this is just the span of these two vectors. 1, negative 2, 1, 0, and 2, negative 3, 0, 1. And we can check that these two vectors are linearly independent, and for that reason these two vectors, just the two vectors here, they form a basis. They are a basis for kernel of T of A, and remember that the kernel of T of A is just the null of A. Let's talk about how to decide if a transformation is surjective or not. Let's consider the same transformation T of A with this matrix, and let me do the picture again. Here we have C4, and here we have C3, and then we can think about what is called the range of the transformation. That means every vector in the codomain that is reached by a vector in the domain. This is called the range. Range of T of the transformation. In this case, the transformation is just T of A. And it's not difficult to check that this range of T is just the span of the columns of A. And the reason is because, just forget about the null, we already computed the null. The reason is that when we do A times X, Y, C, W, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you multiply this by X, Y, C, W, you can check that this is just X times the vector 1, 5, 9 plus Y times 2, 6, 10 plus C times 3, 7, 11 plus W times 4, 8, and 12. And therefore, when you think about every possible outcome that can be produced like this, since X, Y, C, and W can be any complex number, essentially I'm considering the span of these four vectors, which is also known as column of A. Then an easy way to see if this column of A gets to fill the whole codomain is by computing the dimension. Then a transformation T of A is surjective if the dimension of the column of A is the same as the dimension of the codomain. Let me write that down. T of A is surjective if the dimension of column of A, which by the way is just the rank of A, is equal to the dimension of the codomain of T of A. Then this is how it works for transformations that are of the form T of A. Let's see in this particular example, if we want to compute the column of A in this case, then the column of A is just the span of the vectors. We need to pick the columns that are associated with the columns that has a pivot in the reduced echelon form matrix. Then this one has a pivot, this one has a pivot, then that means that I have to pick the first column and the second column, and they expand the whole space. Then here we take 1, 5, 9 and 2, 6, 10. This means that this column, you can get rid of it because this column can be written as a combination of these two, and this column can be written as a combination of these two columns. Then the column of A is just the span of these two vectors. These two vectors are linearly independent, and therefore the dimension of column of A is 2, which is the rank of A, and the dimension of the codomain, remember that the codomain is equal to the number of rows of the matrix. In this case, this matrix has 3 rows, and we get that the rank of A is not the number of rows of A. That means that this transformation T of A is not surjective. Then that's the way we check if a transformation of the form T of A is surjective. Then in this example, the transformation T of A associated with this matrix is not injective because the kernel has dimension 2. In this case, the dimension of the kernel is called the nullity of A, has dimension 2, and is not surjective because the rank is 2 and the number of rows is not 2 but 3. We can generalize this for any linear transformation between vector spaces. Let me write down the theorems. Then this is the situation. We have T, a transformation from a vector space into another vector space. Let's suppose that this is a vector space of dimension n, and let's suppose that we have a basis. We can pick any basis. Let's pick any basis. In this case, dimension of V is n, and here this is a vector space of dimension m, W1, Wm, and in this case I'm saying that the dimension of W is m. Then the way to decide if this transformation is injective and surjective, what we need to do is we need to find the matrix that represent this transformation with respect to these two bases. You can pick any basis and you will get the same answer. Then we pick this matrix. Let me write it down. Matrix that represents T with respect to bases, let's call it B1 and B2. This is B1 and this is B2. Remember that this matrix is easy to find. Essentially that matrix, it has n columns, and the first column is the representation with respect to the basis B2 of the vector T of B1. T of B1 is a vector here in W, and since this B2 is a basis, I can write down that T of B1 as a linear combination of these vectors. Then the weights are the coordinates, and that's called the representation, and that's going to be the first column. The last column is going to be the representation with respect to the basis B2 of the vector T of Bn. And this is going to be an m by n matrix. Then we have that, let me write the theorem. T is injective if the nullity of A is 0. This is part 1. Part 2, T is surjective if the rank of A, which is the dimension of column of A, remember that the nullity is the dimension of null of A, rank is the dimension of column of A, is equal to the number of rows of A. This is part 2. Remember that the number of rows of A is M, which is the dimension of the codomain. More than that, we can find a basis for the kernel of T. Let me write that down. To find a basis for kernel of T, then what we do is we find a basis. Step 1, we find a basis for null of A, and that basis is going to be some vectors. Let's say they are going to be the vectors C11, C1. Those vectors are in Cn, and then CK1, CKN. We are assuming that the nullity of A is K, and for that reason this basis has K vectors, right? And then step 2 is just to write the basis for kernel of T. That basis is going to be the vector, let's call it U1 equal to C11 B1 plus C1n Bn, and then UK is just CK1 B1 plus CKn Bn. Then this is how we find a basis for kernel of T. Notice that something that is very interesting and useful is that the nullity of A, which is K, which is the dimension of the null of A. Remember that A is the matrix that represents the transformation with respect to some pair of bases. This nullity of A is just the dimension of kernel of T. Let's see an example where we can use all of this. Let's suppose that we have this transformation T from the space of polynomials of degree 2 into C2. And let's suppose that this transformation is given by T of P equal to P of 2, P of negative 1. This is a polynomial. I can evaluate it at 2, and then I get a complex number. And here, if I evaluate that polynomial at negative 1, I get another complex number. Let's take some challenging bases for P2 and some challenging bases for C2 so that things becomes a little more interesting. Let's take B1 equal to the basis 2 minus 5x, 1 plus 2x, and 1 plus x squared. And let's take, for on a basis for C2, let's take the vectors 3, 4, and 2, 1. Then, if we want to compute the kernel of T and to decide if this transformation is injective and surjective, then we need to compute the matrix that represents this transformation with respect to any pair of bases will work. And just to make it challenging, I choose this pair of bases. Then let's compute that matrix. To compute the first column of A, we need to compute t of this polynomial, 2 minus 5x. And by definition, we get these two numbers. When I evaluate this polynomial at 2, I get 2 minus 10 is negative 8. And when I evaluate this polynomial at negative 1, I get 7. That means that this is the output. This is, if I call this B1, B2, and B3, this is t of B1. But then I have to write this vector as a linear combination of the bases on B2 to find the coordinates. Then I write it as alpha 1, 3, 4 plus alpha 2, 2, 1. Let me erase this. Remember, the transformation is going to be injective if and only if the nullity of A is 0. Let me just say that this transformation is not going to be injective. The reason is that the dimension of the matrix that we are finding, this is going to be a 2 by 3 matrix. And if we have a 2 by 3 matrix, then for sure when we solve the homogeneous system that we need to solve to find null of A, there is going to be a free variable, and for that reason the nullity is not going to be 0. Then this is not going to be injective. There is going to be a kernel given by the span of some vectors, of a vector. Then we have this, and surjective. To be surjective, we want the rank of the matrix that we are finding to be equal to the number of rows in that matrix. Then when we solve this system, 3 alpha 1 plus 2 alpha 2 equal negative 8, and 4 alpha 1 plus alpha 2 equals 7, we can solve it explicitly, and we get that alpha 1 is equal to 22 over 5, and alpha 2 is negative 53 over 5. That means that the first column of the matrix that represents this transformation with respect to these two bases is this vector 22 over 5, negative 53 over 5. Now, how do we find the second column? We have to compute t of B2, that means t of 1 plus 2x. And this is just, by definition, is this polynomial evaluated at 2. That means when we replace x by 2, we get 5. And when we replace x by negative 1, we get 1 minus 2 is negative 1. And then we need to find the coordinates of this vector in the codomain with respect to these bases. And then we write it as a linear combination of these two vectors, and then we solve the system, which is 3 alpha 1 plus 2 alpha 2 equal 5, and 4 alpha 1 plus alpha 2 equal negative 1, and the solution for that system is alpha 1 equal negative 7/5, and alpha 2, 23/5. That means that the second column of this matrix is negative 7/5 and 23/5. Finally, to compute the third column, we evaluate t of the third vector, and that is t of 1 plus x squared. This is just equal to this polynomial evaluated at 2, we get 5. That polynomial evaluated at negative 1, we get 2. And then we need to find the coordinates of this vector with respect to these bases. Then this is equal to alpha 1 3/4 plus alpha 2, 2, 1, and you end up with this system. 3 alpha 1 plus 2 alpha 2 equal 5. 4 alpha 1 plus alpha 2 equal 2. And the solution for this system is alpha 1 equal
negative
1/5 and alpha 2 equal to 14/5. That means that the third column of this matrix is 1/5 and 14/5. Now we have the matrix. Let's compute the kernel of T. Remember, to compute the kernel of T, we need to follow these two steps. We just need to find the null of A, and then find a basis for the null of A, and produce the basis for the kernel of T. Let's do that. To find the null of A, we do row reduction to this to get the reduced echelon form, and then we end up with the matrix 1, 0, 5 ninths, 0, 1, 17 ninths. That means that to compute the null of A, we have to solve this system. x1 plus 5 ninths of x3 equals 0, and x2 plus 17 ninths of x3 equals 0. x3 is free, and the null of A is in C3. It is built out of vectors in C3, and then x1 is just negative 5 ninths x3, x2 is negative 17 ninths x3, and x3 is a free variable. Then we just write x3 such that x3 is a complex number. And this is just the span null of A, is just the span of this vector, negative 5 ninths, negative 17 ninths, and 1. This vector is also a basis. And then now let's move to step 2. The dimension of the kernel of T is 1. And that basis for the kernel of T, it must be an element in the domain. It must be a polynomial. What polynomial is that? You use these numbers as weights with respect to this basis. Then the kernel of T, let me write here. Let me just write that kernel of T, or let me write a basis for kernel of T is the vector negative 5 ninths, vector v1, which is 2 minus 5x, first element here times the first vector v1, minus 17 over 9 times 1 plus 2x, and then plus 1 times 1 plus x squared. Let's see what polynomial is this. We have negative 10 ninths, negative 10 ninths, minus 17 ninths, plus 9 ninths, and then plus, what is the coefficient of x? 25 ninths, minus 34 ninths, x, and then plus x squared. What polynomial is this? This is negative 10 minus 27 plus 9 is negative 27 over 9 is negative 3 plus 1 is negative 2. 34 minus 25 is 9. Then here you have negative 9 over 9, which is negative x plus x squared. That means that a basis for kernel of t is the polynomial negative 2 minus x plus x squared. Notice that when you think about this vector in P2, you can check that this vector goes to 0, 0. This polynomial, which is a vector in P2, when you apply t to that polynomial, it says you need to evaluate that polynomial at 2. When you evaluate at 2, you get negative 2 minus 2, negative 4 plus 2 squared, negative 4 plus 4, it goes to 0. And when you apply a negative 1, then you get negative 2 minus negative 1 is negative 2 plus 1, and plus another 1, you get 0. Then this goes to 0, 0. Also, any multiple of this polynomial will go to 0, 0. Kernel of t is the span of this vector of this polynomial. Let's check if this transformation is surjective. Remember that the criteria to be surjective is that the rank of this matrix, it must be equal to the number of rows of A. Let me write that here. Is T surjective? Then the question is the rank of A equal to the number of rows of A? How do we find the rank of A? The rank of A is essentially the number of pivots in the reduced echelon form of the matrix A. Here we have 2 pivots. That means that the rank is 2, and we also have that the number of rows of A is 2. Then since this is true, then we have that T is surjective. And the answer is yes. T is surjective.